Let's move on to some autonomic drugs. Hopefully you're getting a little excited now because we can finally cover some drugs. Instead of just covering the concepts behind things, we can finally talk about some actual drugs. But to better understand some of these autonomic drugs, we need to first focus on the nerve terminal and then also a nerve synapse. So let's bring those in here. How are neurotransmitters like acetylcholine even made? Well, within the presynaptic nerve terminal, or the end of the neuron, we'll need to synthesize a neurotransmitter, store it in a vesicle, release that vesicle into the actual synapse here, and then somehow finally degrade or reuptake the neurotransmitter. Now, all of this occurs at the end of the neuron, or the nerve terminal, as pictured here. There are various drugs that can interfere with these different steps. So let's go ahead and start off by looking at our cholinergic nerve terminal. So choline is going to be taken into the neuron from the extracellular space and combined with acetyl-CoA by choline acetyltransferase to produce acetylcholine. So a lot of things just happened there. Let's go ahead and do that again. Our acetyl-CoA and our choline are going to meet through our CHAT enzyme, or the enzyme called choline acetyltransferase, and that'll actually produce our acetylcholine. So there we go. We have our acetylcholine produced. Now remember from biochemistry that glycolysis transforms glucose into pyruvate, which is then converted by pyruvate dehydrogenase into our acetyl-CoA. So that's where we got that. But now we ended up with our neurotransmitter, our acetylcholine. So we can bring in our first drug of the pharmacology section, hemicolinium. Hemicolinium can compete with choline in this step as seen here and prevent the choline from actually being taken up into the presynaptic neuron. Once acetylcholine has been made, the next step is to package it into presynaptic vesicles. And here in the figure I enlarged this purple vesicle so it can show acetylcholine getting packaged into these pre-made vesicles, which will then travel to the end of the nerve here. So these are all packaged acetylcholine vesicles, and they're all just waiting to be released. So our next drug is going to be visamicol. Visamicol can compete with acetylcholine in the packaging step and prevent it from actually being packaged into the vesicles. So finally we have a depolarization of our nerve terminal. We have some sort of action potential which causes depolarization, and we have a nerve stimulation. So it's going to cause our calcium to enter the cell through voltage-dependent calcium channels, which leads to our influx of calcium. The influx of calcium leads to the release of our vesicles, and it fuses with the membrane, the presynaptic membrane, causing the release of acetylcholine into our synaptic cleft. So a lot of stuff has happened so far. We can introduce yet another drug, botulinum toxin. So botulinum toxin inhibits synaptobrevin, a snare protein, and that's going to mediate the fusion of these vesicles with the presynaptic membrane, causing the release of our vesicle. So botulism is going to prevent acetylcholine release at the cholinergic terminals. This is going to prevent muscle contraction, which leads to a flaccid paralysis. Sweating is mediated by muscarinic acetylcholine receptors as well, so botulinum toxin actually prevents sweating as well. And now once in the synaptic space, our acetylcholine can then bind to a postsynaptic receptor to mediate some effect. So here we have our nicotinic receptor, for example. These acetylcholines will go and activate some downstream receptor. So it can also be enzymatically degraded by acetylcholinesterase, which is going to split acetylcholine into our choline and our acetate. So you can see that here. If it doesn't stimulate a receptor, or if once it's done stimulating the receptor, it'll get broken down by the enzyme acetylcholinesterase. Choline can then go on to be reabsorbed and recycled back into the presynaptic nerve. So now that we've come up with the synthesis of acetylcholine, let's go ahead and take a look at the noradrenergic synapse. The noradrenergic synapse, so that's what we have here. How are the catecholamines synthesized? Well, our noradrenergic neuron is where the catecholamines such as dopamine and norepinephrine are assembled, packaged, and released. First, the amino acid tyrosine, a precursor for all catecholamines actually, is going to be transported into the synapse. Once inside, tyrosine is converted to dopa and then further to dopamine. A tyrosine analog called metyrosine can interfere with this step by competitive inhibition. Metyrosine was actually first used as an antihypertensive, but because it non-selectively blocks all catecholamine synthesis, it has a wide range of side effects and therefore is rarely used today for purposes other than research and to talk about conceptually here. So dopamine, once it's synthesized, gets converted into norepinephrine, where it gets packaged into vesicles and can be released into the synaptic cleft. Here, the vesicles containing norepinephrine will be purple spheres again. So we have a drug called reserpine, another drug that can cause catecholamine depletion. Reserpine inhibits the packaging of catecholamines into the presynaptic vesicles. Guanethidine replaces norepinephrine inside the vesicles and also decreases the amount of norepinephrine from the synapse. And then beryllium also blocks the norepinephrine release. So in summary, metyrosine, reserpine, guanethidine, and beryllium have different mechanisms of actions, but they all work to decrease sympathetic outflow by decreasing the norepinephrine neurotransmitter release. So just like in the cholinergic neuron, an action potential will cause the release of our norepinephrine from the presynaptic neuron. And once in the cleft, our norepinephrine will act on the receptors, causing some sort of effect. Some drugs actually increase the concentration of norepinephrine inside the synaptic cleft, leading to an increase in sympathetic outflow. So have you ever wondered how cocaine works? Well, cocaine, tricyclic antidepressants, and amphetamines all increase the amount of norepinephrine in the synapse, as you can see here, and prevent its reuptake into the presynaptic neuron. Amphetamine and ephedrine also stimulate norepinephrine release into the synaptic cleft as well. So all of these drugs we can see have different mechanism of actions. Some block the synthesis and release of norepinephrine. Some stimulate the release and block the reuptake of the norepinephrine. So how does a cholinergic neuron and a noradrenergic neuron differ? A crucial difference between the cholinergic synapse and the noradrenergic synapse is based on the reuptake of the neurotransmitter. So let's take a look at that now. Let's clean everything off, and now we'll start with a new diagram where norepinephrine has already been released into the synaptic cleft. Norepinephrine is absorbed into the presynaptic membrane without being broken down first. So let's recall that acetylcholinesterase is going to break our acetylcholine down in the actual synapse of the cell into both choline and acetate. Norepinephrine, on the other hand, is going to be reabsorbed into the neuron without being broken down first. We have these enzymes, MAO and COMT. These are the enzymes that are responsible for breaking down our catecholamines, such as norepinephrine. But these will be actually located inside the neuron, not in the synaptic cleft itself. Therefore, the main method for clearing norepinephrine from that synaptic space is going to be reuptake. In addition to reuptake from the cleft, note that the release of norepinephrine from the sympathetic nerve ending is modulated by norepinephrine itself via the alpha-2 receptors. So remember what the function of alpha-2 receptors were? Yeah, alpha-2 receptors, when stimulated, are going to decrease sympathetic outflow. So when alpha-2 receptors are stimulated, it'll actually provide negative feedback and reduce the sympathetic outflow and decrease the release of norepinephrine. Activation of the M2 receptors by acetylcholine also inhibits norepinephrine secretion, while activation of the angiotensin II receptors are going to increase norepinephrine secretion. So as you can tell, the body is a complex system of checks and balances. Make sure that you're comfortable with how neurotransmitters are synthesized, broken down, and regulated because these topics make great board questions. Here's another question for you. What enzyme is responsible for the formation of acetylcholine? And what are its two substrates? Well, we just covered the formation and degradation of acetylcholine, so this should be a pretty easy one. If you're struggling with this question, I recommend going back and reviewing this pathway one last time. So the enzyme that forms acetylcholine is choline acetyltransferase, also known as CHAT. It takes acetyl-CoA and choline and converts it into the neurotransmitter acetylcholine here in this equation. So I'll pose another question to you. What enzyme is responsible for the breakdown of acetylcholine? Well, that would be acetylcholinesterase, or ACHE. So this is going to be a very important enzyme that we'll spend a lot of time later on in the lecture over this enzyme here, acetylcholinesterase.